Welcome to Ms. Taylor's class notes for honors geometry. Today we're going to be talking about some new postulates and how to interpret diagrams that we see and to even draw our own diagrams. So real quick, one fun fact: postulates are things that we know are true. They have been tried and tested over and over again in geometry, and these are things we know are fact. First unit, we learned 3 different postulates, if I remember correctly. We learned our ruler postulate, which just means if we have a number line, those numbers correspond to real numbers in the real world. We learned our segment addition postulate, where part plus part equals whole. And we learned our angle addition postulate, where part plus part equals the whole angle. And so those are the 3 postulates we've talked about so far, and now we're going to talk about more. So here on the left-hand side are going to be our postulates, and then we're going to have a visual example as well as a written example. I'm going to focus primarily on the text of the postulate and the visual, but you've got those examples in words as well using the diagram. So the first one we're going to look at, these 2 postulates both go with this picture. And think of these postulates as the converse of each other. So they say the opposite thing in an opposite direction. So our 2-point postulate says if we have 2 points, then we have a line. So we have point A and we have point B. And so because we have 2 points, we are able to draw line L through those 2 points. Now, the converse, or the one in the opposite order, is our line-point postulate. A line has 2 points. So because we have line L and we've drawn out a line, we know that line has to contain 2 points. So next we're looking at our line intersection postulate. So if, then, a lot of these are going to be written as conditional statements. That means we can think about their converse, we can think about their inverse, we can think about their contrapositive, and we could even, some of them, turn them into a biconditional statement. So if 2 lines intersect, so I have line M and I have line N, and they go through one another, then their intersection is always going to be 1 point, which in this case is point C. So lines can only meet at 1 point. All right, so these 2 are also going to be converse of each other, and they go together with this picture here. So our 3-point postulate says that if we have 3 non-collinear points, non-collinear means not on the same line, then we have 1 plane. So if we look at this picture, we have points E, point D, and point F, and because we have 3 points and we cannot draw 1 line through all of them, then we have 1 plane, plane R. So the converse of that, or the put in the opposite order, is a plane contains 3 non-collinear points. So if we start with plane R, we know for a fact that there are at least 3 non-collinear points. All right, our point line postulate. Again, we have a conditional statement, if, then. So if 2 points are on a plane, then the line is also on the plane. So if we have points D and points E on plane R, then we know that line DE is also on plane R. All right, our final one, our plane intersection postulate. If 2 planes intersect, then their intersection is a line. So these 2 planes meet at line L, and that line is where they intersect. So now we're going to apply these things to diagrams and different things that we will see this year in geometry. So again, we have our if-then statement. So if we have 2 or more points, A, B, and C, then we have a line. So which postulate or theorem tells us that if we have 2 or more points, we have a line, that's going to be our 2-point postulate. So now if we look at this, our if, then, so if we have a plane with 3 non-collinear points, so we have a plane, we have 3 non-collinear points, then we know we have a line, and that line is also on that plane. So this one is going to be our plane line postulate. So now we're going to use this picture here to help us write some examples of these postulates. So our 2-point postulate says that if we have 2 points, we have a line. So we're looking for 2 points on this that create a line. So I have point B and I have point C. So points B and C create line BC. And I'm going to use my line notation with the line above the 2 points on the line. So our line point postulate is the converse of that. So if I have a line, line L, contains 2 points B and C. I'm going to use the and symbol, B and C. So our plane point postulate tells us that a plane contains at least 3 non-collinear points. So I need to look at my planes. If I notice, plane Q only has 1 point, plane C. So I cannot use that plane for this theorem because it has to have 3 non-collinear points. So now we look at plane P. A is not on the line with B and C, so that gives me 3 non-collinear points. So plane P contains points A, B, and C, which are non-collinear. So our plane intersection postulate tells us that planes intersect at a line. So if I follow Q, it seems to stop at that line, and if I follow P, P also seems to stop that line. So planes P and Q intersect at line K. All right, so the next thing that we often do in geometry is we have to read diagrams and we have to interpret them and we have to know what we can and cannot assume. I always like to talk about in geometry, we can never assume anything. Geometry is all about what do we know for a fact and what can we prove. So we're going to see if we can prove these statements based on the postulates and theorems that we know. So planes A and B, so I have plane A and I have plane B, intersect at EF. So here is line EF. So it looks like, yes, that's where those planes intersect. So yes, because of our plane intersection postulate. And I'm going to abbreviate postulate, P-O-S-T. So now it's asking if points C and D are collinear. So collinear means they are on the same line. So I need to find C and I need to find D. I do not see a line between them, so I do not know if they are collinear. So no, they are not on a line. So I'm going to erase some of these markings because it's going to get, oh no, that was not my eraser because it's going to get confusing. Give me a second. Okay, so our next one is ray. Come on, pencil. Ray HJ. I had to use the word ray because Microsoft and Google don't let me put the ray symbol above HJ. So H is going to be our endpoint and J is going to be our arrow. So we're talking about ray HJ and line ID. So I follow D and I'm going to go all the way to the arrows. Are perpendicular. So perpendicular tells us a 90-degree angle. And we know that these boxes right here mark 90-degree angles. So yes, We know this because of the right angle symbol. All right, so the next one we're going to look at is line GD. So I'm going to highlight GD. All right, I'm going to highlight the whole thing. A bisector of line EF at point D. So bisector means cut in half. So if I look closely at this diagram, I have my congruent markers there. So yes, ED is congruent to DF because we have our congruent markers. So the next one that it's having us look at is our lines IH, line segments IH, and line segments HG equal. So we don't have those same congruent markers. They did not put those on there, so our answer is going to be no because there are no congruent markers. And this is kind of the part of geometry where it becomes one big puzzle, and it depends on the information that you know, what you can prove and what you can solve. So here we're looking at angle HJD. So H, I'm going to trace it to J, to D. So we're going to talk about that angle there, and HDJ, we're going to talk about that angle there. So it's asking if they are complementary, which means they add up to be 90 degrees. So first look, there's nothing that tells us they're 90 degrees, but if we put on our geometry hat and our math problem solving, we know that this right here is a triangle. We know that triangles equal 180 degrees. So if angle JHDG equals 90 degrees, I'm going to subtract that from 180, and I know the other two angles have to equal 90 degrees. So yes, because of all of this information here that I just told you. And now we're going to work on drawing different diagrams, making sure that we understand what these things mean and what they say so that we can have an accurate understanding of what's going on. So we have ray RS. Again, I'm going to draw that ray symbol over there to help me draw it better, and then line KL. So I'm going to start by drawing line KL. It's just a lot simpler and a lot easier to draw the line first. Our next vocab word is bisect. So ray RS is going to bisect at point R. So I know that R is going to be the thing that divides it in half. And I know that the R is also going to be where my ray goes. So that's point R, which means somewhere over here needs to be point S. So here we've got line AB in plane U intersecting line CD at point E, and point C is not on plane U. So I'm going to draw plane U first because that's the big thing that we need to make sure we have on there. We know that line AB is on plane U. So put my points on there, make sure it's labeled. So we know that CD is going to intersect AB at point E. So I'm going to go ahead and draw point E. But it tells us that C is not on the plane. So what I'm going to do is I'm going to draw an arrow coming towards us, and I'm going to put C there, and I'm going to do a dotted line to show that that line is actually behind the plane and not on the plane, and that's where I'm going to put point D, because it's on the line behind the plane, not actually on the plane. All right, I want you to use your notes from Unit 1 to draw a linear pair, and I want you to use your notes from Unit 1 might help you, or look at our other examples and our other postulates, and I want you to draw this one here. Check with the completed notes to see if you got it right. All right, now for the more complicated ones. So we have two planes that intersect. There's a couple of different ways we can draw planes that intersect. If we look at the example in our notes, we can kind of draw a plane here and have it go that way, and then have a plane come this way and have our dot dot. And actually once we get out, or we could always draw planes that meet at an X, and then we would have this one come back here, that one would keep going, you can have this one come here. So there's a couple of different ways we can draw planes intersecting. So they're going to intersect at AB. So I can have this right here, BA, B, or I can have this right here, B line AB. And then we need point E. Ooh, I forgot to label my planes. Let's call this one plane C. Let's call this one plane D. Let's call this one C, and that one back there D. And then we need point E on plane C. So there's point E, there's point E. Okay, I want you to try this one on your own, and I want you to look at the completed notes to see if you got it right.